Hey guys, welcome to the second video in our series on combinatorics. In the previous video, in part 1, we covered the basics of combinatorics in an intuitive way. And in this session, we will build upon that knowledge such that at the end of this video, you will be able to calculate the probability of drawing any combinations of cards from a standard deck. But before we get there, we will be solving exercises step by step, increasing in complexity. The timestamp for each exercise can be found in the comment section below. And as always, if you have any questions along the way, feel free to ask them in the comments down below or join the community and visit our Discord server where you can freely interact with fellow students and myself. Also, you can show your support by giving this video a thumbs up, which helps out tremendously. And with that said, let's get into the exercises. And in particular, all of the exercises that we will consider will revolve around the same scenario, namely where you have to draw 8 cards from a deck of 52 cards given a specific constraint. For example, 2 of the 8 cards have to be a 10 and the other cards have to be hearts. And then given this constraint, we need to calculate the number of combinations in which you can have 8 cards with the given constraints. But before we get to these exercises, let's first, as a warm-up exercise and a recap of the previous video, calculate the number of ways in which these 8 cards can be drawn without any constraints. So basically calculating the number of combinations in which we can draw 8 random cards from a deck of 52 cards. And to approach this problem in a more visual and tangible way, let's first draw our 8 cards. And before we actually dive into the calculations, let me first stress that in this exercise and all of the following exercises, the order of the cards does not matter. For example, if you draw the 8 cards from the 2 of diamonds all the way to the 9 of diamonds, then this would be exactly the same as drawing these 8 cards in a different order. They all count for the same combination of cards, since the only thing that matters is that we have exactly these 8 cards in our hand. And let's now do the actual calculations by considering the number of choices we have for each card. And this goes as follows. For the first card, there are of course 52 possible outcomes, since we have 52 cards to choose from, and therefore we have 52 choices for this first card. If we now look to the second card, we only have 51 cards to choose from, since we already picked one card out of the deck. This means that for the second card, we have 51 choices. Likewise, for the third card, we have 50 possible outcomes, so 50 choices. For the fourth card, there are only 49 choices left, because there's only 49 cards left to choose from. 48 for the fifth card, 47 for the sixth, 46 and all the way to 45 choices for the last card. And then in order to get the total number of choices or the total number of combinations, we simply multiply all of these numbers together from 52 all the way to 45. And at this point, we need to take into account that the order of these 8 cards does not matter. The only thing that matters is that we have exactly these 8 cards in our hand. Now, to take this into account, we need of course to divide this multiplication of all of these numbers by the number of ways in which we can shuffle around 8 cards. And this is exactly 8 factorial. And this exactly gives us the number of combinations in which we can draw 8 random cards from a deck of 52 cards. Writing this down, we have 52 multiplied by 51, multiplied all the way down to 45. And we divide this enumerator by 8 factorial to take into account that order doesn't matter. However, as we have seen in the previous video, we can write this in a more general form. In the enumerator, we can write 52 factorial. And then we divide this, of course, by another large number, because 52 factorial has a lot of terms that we didn't have in this first enumerator, namely the multiplication with 44, with 43, all the way down to 1. Therefore, we have to divide away all of these extra terms by dividing by 44 factorial. And then of course we multiply with this 8 factorial, which we simply copy. This can then again be rewritten in a form that only contains numbers that are fundamental to our problem. We have of course 52 factorial because, well, we have 52 cards to choose from. And we divide this 52 factorial by 52 minus 8 factorial multiplied by 8 factorial. And we see that this 52 minus 8 is simply 44. And thus we see that we've rewritten our problem here, the number of combinations, as a fraction of numbers that are inherent to our problem. We have 52 cards to choose from, and we pick 8 cards. Running this through a calculator, we get the exact amount of combinations. 752,538,150 possible combinations of drawing 8 cards from a deck of 52 cards. And this is without any constraints. And if you're already confused at this point, I gladly refer you to the previous video, part 1, where we build up all the way from the very basics to this point. Let's now increase the complexity a bit and go through the cases where we add constraints to these 8 cards. And we will start with the easiest case, where we say that from these 8 cards that we draw from our deck, exactly 3 of them have to be aces. And then the exercise, of course, is to calculate the number of combinations of 8 cards, of which 3 are aces. And again, the first step is to make it more visual and to draw our 8 cards again. And now let's see what constraint we actually have. We know that 3 of the 8 cards have to be aces. And then the remaining 5 cards can be whatever cards, but they cannot be aces, because if one of these cards is an ace, that would mean that we have in total 4 aces. And the constraint was that we exactly need 3 aces. So these 5 cards can be whatever, but just no ace. Let's for instance look at some examples of these 3 aces that need to be present. For instance, it could be the ace of clubs, the ace of spades, and the ace of hearts. However, it could also be the ace of diamonds, the ace of hearts, and the ace of spades. And since order does not matter, this combination would be the same as the ace of spades, the ace of diamonds, and the ace of hearts. And let's now do the calculation by again using our systematic way of looking at the number of possible outcomes, or the number of choices for each card in our series. For the first card here, we know that it has to be one of the 3 aces, which means that at this point we have 4 choices for this first card, since there are 4 possible aces in a standard deck, which means that there are 4 possible choices. This means that for the second card, which also has to be an ace, we only have 3 choices left, because we already picked 1 ace, which means that there is 1 less ace to pick from, so only 3 remain. And then for the third ace, we of course only have 2 choices left. Now for the next card, we know that it can be whatever card possible, however it should not be an ace. So how many possible choices do we have here? Well, we know that we start with 52 choices, because a deck of cards contains 52 cards, but we have to subtract 4 because we cannot choose an ace, and there are 4 aces in a deck. So this means that we only have 48 choices left. This of course means 47 for the second card, because we already picked 1 card, 46 for the third, 45 for the fourth card, and 44 choices left for the last card. And as stated before, the total number of combinations is now simply multiplying these numbers together, and of course taking into account that order doesn't matter. So what does this look like? Well, we have 4 multiplied by 3 multiplied by 2, which is of course these 3 aces. Now since the order doesn't matter, as we seen in this specific example, we have to divide this by the number of ways in which we can swap these 3 cards around. This is exactly 3 factorial ways. And then we multiply this with the number of combinations of these remaining 5 cards. This is of course 48 multiplied by 47 multiplied by 46 times 45 times 44. And taking into account that the order does not matter, we have to divide this by the number of possible ways in which we can shuffle around 5 cards. This is exactly 5 factorial ways. And we see something quite interesting happening here, namely that the total number of combinations in which we can draw 8 cards from a deck of 52 cards, of which 3 of them are aces, separates into 2 problems. Namely a first problem where we have to draw 3 cards out of a possible pool of 4 choices, namely 4 aces. And then the other problem where we have to draw 5 cards out of a pool of 48 cards, namely the total number of cards in a deck minus the 4 aces. And this separation of problems will help us to quickly calculate the number of combinations with any arbitrary constraint. Let's now calculate the exact number that we get. We have for the first problem 4 factorial divided by 4 minus 3 factorial, since we have 4 choices and are drawing 3 cards, multiplied by 3 factorial, because order does not matter, and this is exactly the number of ways in which we can shuffle around 3 cards. Then we multiply this with the second problem, and we multiply this with the second problem, where we have 48 possible choices, so 48 factorial in the enumerator, and we divide this by the following: 48 minus 5 factorial, since we have 5 cards that we need to choose, multiplied by 5 factorial, because order doesn't matter, and 5 factorial is the number of ways in which we can shuffle 5 cards around. Plugging this into a calculator, we find a total number of 6,849,216 possible combinations in which we can draw 8 cards from a standard deck, of which exactly 3 are aces. Being more familiar now with the systematic approach of counting these numbers of combinations, let's go to the next exercise, where we again increase the complexity a bit. In this case, the constraint that we have for these 8 cards is that at least 3 of them have to be aces. Now note the difference with the previous exercise, where exactly 3 cards had to be aces. And again, to make this more visible and thus easier to solve, let's again draw our 8 cards. Now, if at least 3 cards of these 8 cards need to be aces, we can recognize that there are exactly 2 scenarios. The first scenario is where exactly 3 cards are aces, and this is exactly the problem that we had in the previous exercise, and we will call this scenario 1. And again, in this scenario, 3 cards have to be aces, and the remaining 5 cards can be whatever, however they cannot be an ace. However, in this exercise, there is of course another scenario, because we know that there are in total 4 aces, and if we have to count all of the combinations with at least 3 aces, this is of course also all of the combinations where there are exactly 4 aces. And this we will call scenario 2, where 4 cards have to be aces, and the remaining 4 cards can be whatever, however they cannot be an ace. But that is not a problem in this case, because we already drawn the 4 aces. So it's actually impossible for one of these remaining 4 cards to actually be an ace. And then the total number of combinations in this case, where at least 3 cards are aces, is simply adding the combinations of the first scenario, where we have exactly 3 aces, to the number of combinations of the second scenario, where we have exactly 4 aces. And let's do that right now, starting with the first scenario, which is of course exactly the scenario that we had in the previous exercise, and we can directly copy its result. So we have 4 factorial divided by 4 minus 3 factorial multiplied by 3 factorial. This is the subproblem of combinations of exactly 3 aces, given that we have a total of 4 aces to choose from, multiplied by 48 factorial divided by 48 minus 5 factorial multiplied with 5 factorial, which is of course the number of combinations of the remaining 5 cards. And we calculated this to be 6,849,216 possible number of combinations. And let's now look at the second scenario, where we have to count the number of combinations where we have exactly 4 aces. And again, let's do this in the systematic way of counting the number of options or possible outcomes for each of our cards. We know that for the first card, we have of course 4 possible choices, namely one of the 4 aces. For the second card, we have 3 aces remaining. For the third card, we only have 2 aces remaining. And for the last card, of course, we don't have any choice at all, because we just have to take the remaining ace. Then going to the subproblem of the remaining cards, where we can easily obtain the number of choices for the first card, which is basically 52, the number of cards in a deck, minus 4, because the 4 aces are already picked out. And therefore, we have 48 choices for the first card, 47 for the second, 46 for the third, and 45 for the last card. And from all of these choices for these different cards, we can directly write down the number of combinations. For the first subproblem, we have 4 times 3 times 2 times 1, divided of course by 4 factorial, which is the number of ways in which we can swap these 4 cards around. And we multiply this by the second problem, which we now directly write into its general form. We have 48 possible cards to choose from in this problem, and we divide this by 48 minus 4 factorial, and this minus 4 is of course because we still have to choose 4 cards, multiplied by 4 factorial because we can shuffle these 4 cards around in 4 factorial possible ways. If we plug this into a calculator, we find 194,580 possible combinations of 8 cards, of which exactly 4 are aces. And then concluding this exercise, we have of course that the total number of combinations in which we can draw 8 cards, of which at least 3 are aces, is of course the number of combinations of scenario 1, where we have exactly 3 aces, plus the number of combinations of scenario 2, where we have exactly 4 aces. And this turns out to be 7,043,796 possible combinations. And let's now go to the fourth exercise, where the constraint is the following. From these 8 cards that we draw, exactly 2 of them need to be kings and 2 of them need to be queens. And again, to solve this exercise, we start by visualizing it and therefore drawing our 8 cards again. So what are the constraints in this case? Well, exactly 2 cards need to be kings. 2 other cards need to be 2 queens. And then the remaining 4 cards in this case can be whatever other card, but it cannot be a king or cannot be a queen. Because if it were a king or a queen, that would mean that our constraint would be violated, because then we would have either more than 2 kings or more than 2 queens. So let's now use this systematic way to solve this exercise by looking at the number of possible choices for each card. For the first card, we can choose between 4 kings. And of course, for the second card, we only have 3 kings to choose from, so we have 3 possible choices. Therefore, the first subproblem will be 4 multiplied by 3 divided by 2 factorial. And 2 factorial is the number of ways in which we can shuffle around 2 cards. But as you know, 2 factorial is simply 2, because we can of course only swap 2 cards around to change their order. For the second subproblem, the constraint of the queens, we have again 4 choices to pick from because we have 4 queens. And for the second queen, we only have 3 choices left. So we multiply our first subproblem again by 4 multiplied by 3 divided by 2 factorial. And let's now look at the last problem of the 4 remaining cards. So how many choices do we actually have for this first card right here? Well, we start of course with 52 choices because there are 52 cards in a standard deck. However, there are of course cards that we cannot choose because we would be violating our constraint. There are of course 4 kings inside of a deck, so -4, and there are 4 queens in a standard deck, so -4. And therefore the total number of cards that we can choose from, is of course 44, namely all of the cards in a standard deck without the kings and without the queens. For the second card we then have 43 choices, for the third card 42, and for the last card 41 choices. Writing this subproblem down in its general form, we have 44 factorial, because we have a total of 44 choices to pick from. In the denominator, we have 44 minus 4 factorial, and this -4 comes from the fact that we are picking 4 cards, multiplied by 4 factorial, because the order doesn't matter. Plugging this into a calculator, we find 4,887,036 possible combinations to draw 8 cards, of which exactly 2 are kings and exactly 2 are queens. And because we are now becoming more proficient in how to solve these exercises, let's go to the fifth and final exercise, where we look at the most complex form of constraints. In this exercise, the constraint is as follows. From the 8 cards that we are drawing, one of them has to be the ace of diamonds. There needs to be exactly 4 clubs and there cannot be any 7s in our 8 cards because, well, you don't like the number 7. And again, to make it visual and easier to solve this exercise, let's for one last time draw our 8 cards right here. We know that one card has to be the ace of diamonds. We also know that 4 of these 8 cards have to be clubs. However, it cannot be the 7 of clubs because one constraint is that there are no 7s in our 8 cards. And then the remaining 3 cards can be whatever without constraint. However, they cannot be a 7 because, well, we don't like 7s, and they cannot be a club because if they were a club, that would mean that we would have more than 4 clubs, which violates our constraint. So let's now use our systematic method to calculate the number of combinations of 8 cards with exactly these constraints. For the first card, we of course only have one choice, namely the ace of diamonds. So that's quite simple. This subproblem simply reduces to the number 1. Then we have to multiply this with the second subproblem, namely that 4 cards have to be clubs. So how many choices do we have for this first card? We know that there are exactly 13 cards of each suit in a deck of cards, meaning that there are exactly 13 clubs. However, we know that we do not want any 7s. Therefore, the 7 of clubs is not an option, and we only have 13 minus 1 choices remaining, and this means that we have 12 clubs to choose from for this first card. 11 remain for the second card, 10 for the third, and 9 possible choices for the fourth card. Again, writing this down in our general form, we have 12 factorial because we have 12 clubs to choose from, namely all of the clubs minus the 7 of clubs, divided by 12 minus 4 factorial because we are picking 4 cards, multiplied by 4 factorial because we can arrange or shuffle around these 4 clubs in 4 factorial possible ways. Then we multiply this with the final subproblem. The 3 cards that can be whatever, however, there should be not a 7 and not a clubs. So how many choices do we have for this first card? Well, let's start again with 52 choices because we have a deck of 52 cards. We subtract 1 because we cannot choose the ace of diamonds anymore. Then we subtract 13 cards because we're not allowed to pick any clubs, because that would violate our constraint that there should be only 4 clubs. And then to end off, we subtract 3 because we're not allowed to pick any 7s. And the 7s that are remaining are the 7 of hearts, the 7 of diamonds, and the 7 of spades, because the 7 of clubs is already contained in this constraint right here. This means that for this first card, we have 52 minus 1 minus 13 minus 3 possible choices to choose from. This comes down to be 35 choices for this first card, 34 for the second, and 33 for the last card. Writing this in our general form, we find that for this subproblem, the total number of choices is 35 factorial, because we have 35 choices, 35 minus 3 factorial, because we pick 3 cards, multiplied by 3 factorial, because we can shuffle these 3 cards around in 6 possible ways. Running this through a calculator, we find a total of 3,239,775 possible combinations of 8 cards, of which one of them is the ace of diamonds. There are exactly 4 clubs and there are no 7s present. And this brings us to the end of this video, and I hope that you're now more familiar with how to solve these problems of combinatorics. If you have any questions, again, leave a comment in the comment section below or join our community Discord server. If you enjoyed this video, give it a thumbs up, and if you want to get notified by future releases, consider subscribing. And with that, I thank you for watching, and I will see you in the next one. Bye.